Good evening, both of you. Am I audible? I'm assuming you can hear me. So I'll just quickly share my screen. Hi, can you see the slideshow mode of the PowerPoint? Either of you? Okay, no issue. So I'll just,
Yes, ma'am.
yeah, thanks. So I guess we'll just continue with this session and see if more people join. So welcome back to the week 4 session of the NPTEL online course titled Drug Delivery Principles and Engineering. And as you know that we are discussing some previous year assignments as well as few top key points that are being discussed in the current course. So I'll just move ahead with the whatever key points are being discussed in week 4 lectures. As you know, we are discussing various drug delivery systems. So in the previous, it's been going on for a month now, and we have in the previous few lectures we have seen what are polymer drug conjugates, wherein if you have a very small molecule, in order to increase its half life in the body, what you can do is you can take a polymer, a long chain of polymer, and conjugate your small molecules to this polymer. Or if you in case have a very big molecule such as a protein, which is also your drug, then you can conjugate peg chains or any other polymer chains to this, so that you can increase its half life in the body, or you can increase its stability, you can reduce the toxicity by avoiding immune reactions because of this polymer drug conjugate. Next, we have seen reservoir systems, which are nothing but a supersaturated drug core which is in a non-degradable membrane. Then we saw its advantages and disadvantages as well. And then we have seen matrix systems, which could be both erodible and non-erodible. Erodible meaning that you make it of such a polymer that it eventually, as time goes on, it starts biodegrading, bioeroding, so you don't have to perform another surgery to remove the implant. Then we have seen something known as hydrogels, wherein these are made of polymers which are capable of retaining a lot of water, and they, because they have a lot of hydrophilic groups, so they attract water, and once they attract water, they'll swell in size, and that's how your drug gets released. So all of these systems are essentially macro systems. You have a macro size implant which you have to perform first of all a surgery to implant it into the patient's body, and then after its time is done, you have to again remove it in case it's non-erodible. So this could be a little cumbersome because patients are usually not very compliant towards performing surgery twice or even once. So in order to avoid that, we have another drug delivery system which is known as micro and nanoparticles. So what you can do is, instead of making a bulk implant, you can now make very very small implants which are either of micrometer or a nanometer range, and these are known as micro and nanoparticles. So these are nothing but, let's say you have a polymer coating and you have your drug encapsulated inside this particle, and the size dimension of these particles is now in either in the micrometer or the nanometer range. So microparticles, so there's no fixed definition of this, but by convention microparticles are can lie anywhere around 100 microns, and nanoparticles are something which are around, let's say, below 100 nanometers in size. So uh, the biggest advantage of having micro or nanoparticles as your drug delivery systems is they are injectable. So you can quickly after your formulations, you can take these micro or nanoparticles in a syringe and you can inject it into the patient's body, rather than making a surgery, implanting it, and then making another surgery to remove that implant. So this is the biggest advantage of having your drug encapsulated into these particles. And also it decreases non-specific delivery. For example, let's say I am trying to treat a disease which affects the lungs. So in that case, if I was going for any of these above mentioned drug delivery systems, I would have to implant it somewhere else in the body, and then wait for the drug to diffuse from that particular implant to the lungs. It will first of all flow into the blood and then go to the lungs, which will then take time for the drug to have effect. Instead of that, if I now have my drug formulated as a microparticle, what I can do is I can make it as an inhalable product. When the patient inhales it, most of it will go directly to the lungs, and since these are very small particles in dimension, they are capable of going to into the deep lungs as well, and that's where they'll deliver the drug. So in that case, it will be a very specific and very targeted delivery. So these are some of the advantages of having micro and nanoparticles. Now, there are various kinds of drugs that could be delivered via micro and nanoparticles. These could be your small molecules, or they could be your proteins. These could be peptides. You can also deliver nucleic acids in this system. And what it is then, as I said, your micro and nanoparticles could be a polymer membrane inside which or it could be a polymer wherein your drugs are encapsulated. Or what you can do is you can also adsorb your drugs onto the surface of these particles. For example, most of the nucleic acids, let's say you have an mRNA delivery, so instead of encapsulating mRNA, you can absorb it on the surface of these particles. So since you know mRNA is negatively charged, so what you can do is you can have a positively charged groups on the polymer surface, and that's how you can have an interaction between the nucleic acid and the polymer surface or your microparticle surface. So that's one way to deliver drugs via these particles. The next points that were discussed in this week was characterization of these particles. So what do you mean by characterization is, once you make these particles, you have to know what size of particles first of all you want, or what could be the shape of these particles. So whenever you say particles, the most obvious thing that comes in our mind is that it will have a spherical shape. So not necessary, you can have, so there was, I guess, a case study discussed in week 4 wherein the authors of that paper have tried making different shape of particles, and they have seen how shape affects the circulating time of these particles. So that's one way of characterizing these microparticles or nanoparticles. Then you have something known as polydispersity. If you people remember, we discussed this concept for polymers. Polydispersity is nothing but it gives you a size distribution. So for example, you can know what size of particles you are and what is the distribution of this size, how many particles are of that particular size. So this is important to know because you would want your formulation of these particles to be very uniform. You don't want different sized particles in the formulation. That will then affect its circulating time, or it can affect the sustained release of the drug from these particles. Next, you have to characterize the carrier composition. For example, this is so as I said, your drug is now encapsulated into the polymer, so you need to know what polymer it is, what is the composition of this polymer, or if you have to additionally put in some surfactants in this composition. So all of this comes under carrier composition. Yeah, next you have encapsulation efficiency. So as I said, your drug is being encapsulated in this particle, so you need to know what is the encapsulation efficiency. This is nothing but you first start with some known amount of drug, and then you encapsulate it into the particle. So how much amount of the original drug has been actually gone into the particle is known as encapsulation efficiency. And next is you need to know the loading levels. So loading levels are a bit different from encapsulation efficiency. Loading levels are how much amount of the particle is actually taken up by your drug. So it's nothing but a ratio of amount of drug to the amount of the particle. So these are some of the ways where you can in which you can characterize the particles. Next, you have the different methods of particle synthesis was discussed in this week. There are various ways to manufacture these particles. It could be single emulsion, it could be double emulsion, there's something known as spray drying, gelation, or hot melt, and there are various other methods as well. So, and the last part discussed in this week was liposomes. This is another drug delivery vehicle. So liposomes are nothing but lipid bilayers which have drugs encapsulated into them. So if you remember how our cell membrane is made, membranes of all our cells, so these are nothing but lipid bilayers, right? They have hydrophobic chains and they have a polar hydrophilic head. So liposomes are nothing but artificially made lipid bilayer, and while manufacturing you can put in lipids which are actually found in our cell membrane as well. So what this does is it will make your liposomes very biocompatible, because now your liposome, this lipid bilayer is very similar to your cell membrane, so your body will think that this is part of the body and it will not have a very strong immune reaction against it. So in that way liposomes are very advantageous as a drug delivery vehicle because they are very biocompatible. But the disadvantage for this vehicle is they are very poor in scale up, because it takes a lot of effort and cost, also a lot of cost goes into manufacturing these liposomes. And since it's a batch process, like you have a limitation on how many liposomes you can make in one particular batch. So batch to batch variability is another problem, but liposomes are something to be explored for various different drug delivery applications. So these are some of the key points that were discussed in this week's lecture. Does anybody have a doubt in this before I move on towards the assignment questions? If not, then I'll go ahead with the assignments. Yeah, so the first question is, what is proton sponge effect? So if you guys have gone through the lectures, I think you'd be able to answer this. Just go through the options slowly, and then remember there are two options correct, meaning we have choose two answers for this particular question. And let me know if anybody knows the answer. If not, we'll discuss.
Option 1 and 2.
Option 1 and 2 are particles carry secondary or tertiary amines which help in escaping endosomal and lysosomal vesicles inside the cells, and it leads to osmotic swelling and bursting of vesicles. Okay, we have one answer. Does anybody else wants to volunteer for this? Thank you for answering. Okay, no other response. Then we'll discuss the answer. I think, yeah, yes, you're correct. The correct options for this particular question is 1 and 2. So you were right in your answer. So let's see what is proton sponge effect. So essentially what happens is, when you have delivered these particles, you want the particles to be uptaken by the cell, or you want the drug that you have encapsulated in these particles to be released inside the cell. So once you deliver these particles, since they're very small, these are micro and nanometer range, all the cells in your body, they have this capacity or ability to uptake these particles by endocytosis. It's a natural process that happens. And once your cells have uptaken these particles, because your cells now don't know what these particles are, they think it's a foreign material, so which obviously it is. So what your cells will do, it will, I think I have a diagram, yeah. So once these cells will uptake your particles, they will be taken to endosome compartment in the cell, which will then be fused, will then convert into a lysosome, wherein all your foreign material and all your cell debris is getting degraded. This is like the waste chamber of your cell, and this is what will happen to your particles if you deliver them. But we don't want our particle to be degraded here. We want the particles to release the drug that you have encapsulated in the cytoplasm of the cell. So to achieve that, what we can do is we can use a proton sponge effect. Now what is this? So to make use of proton sponge effect, what we can do is this, the polymer that you have used in making your particle, you can choose it in such a way that it will have a lot of tertiary and secondary amines. You know amines, right? These are NH2 groups, so secondary amine and tertiary amines. So if you have these in your polymer, what will happen is, once they are fused with this lysosome, once your particles are inside the lysosomes, since the pH of this lysosome is very acidic compared to what is there in the cytoplasm, so it will have a pH of somewhere around 4 or 5. So at this acidic pH, your NH2 groups, your secondary and tertiary amines, they are going to start sequestering the H plus that are present in this particular chamber. Now because they are sequestering, they are taking up all the H plus here, there will be very less H plus remaining in this lysosome, which will now disturb the pH of this particular compartment. So now your cell thinks that something is going wrong with the lysosome, so it starts pumping in more and more H plus, which you can see are coming through this channel. So more H plus will come inside, and to balance that charge, now more and more chloride ions will also come inside. Now what all of this leads to is, now there will be a lot of charges inside this lysosome compared to what is there in the cytoplasm. So this will disturb the osmotic balance of the cell, and the cell will then try pumping in water from the cytoplasm to into the lysosome. So now there is a lot of water here, there are a lot of charges here, so all of this will create a tension and will create it will exert a lot of pressure on the membrane of this lysosome, and in this process, because of all the tension and all the osmotic pressure, the lysosomes will burst, and all your particles, without being degraded, they will be released in the cytoplasm, from where now your drug could be released. So this is the proton sponge effect. So if you read the options, you'll get to know the answer. So your particles carry secondary or tertiary amines which help in escaping endosomal and lysosomal vesicles inside the cells. So this is known as endosomal escape of particles using the proton sponge effect. And this phenomenon actually leads to osmotic swelling and bursting of the vesicles. So this is one of the methods to take advantage of if you want your particles to escape the lysosomal vesicles. Is this clear? Let me know if I'm going too fast, rushing in with the explanation, and I can slow down a little and explain it again if you people want it. If not, then I'll go to the next question. Shall I? Okay, I'll take up the next question then. So the next question is, which one is not correct about dendrimers? So there are several options given here, only one option is correct. Read through the options and let me know if anybody has the answer. Remember to read the question carefully. It's asking us what is not correct about dendrimers. Any volunteers?
Second option.
They are generally not more than 100 nanometer in size. Okay. Anybody else? Thank you for answering. No other response? Okay, we'll look at the answer then. The correct answer is they are generally more than 100 nanometer in size. I'll walk you through this. So dendrimers are nothing but these are tree-like polymers which start from a central core and then they branch out and look something like this. So this is known as a dendrimer. It is another drug delivery vehicle, and these are actually not more than 15 nanometer in size. So that's their size range. And so we'll go through the options one by one. So they are tree-like polymers branching out from a central core and subdividing into hierarchical branching, which is actually correct. That is what dendrimers are. They are generally not more than 100 nanometer in size, which is actually the correct thing. They are usually somewhere around 15 nanometers. So this option is correct. So the question is asking us what is not correct about dendrimers. So it has a very dense surface surrounding a relatively hollow core is also correct. They are very high in molecular weight. The entire structure can be divided into generation of shells. So these have these you can call it as different generations. Each shell will be a different generation. And what are the other options? Yeah, branch density increases with each generation. The size of dendrimer depends on the number of generations, which is also correct. The last option is they're generally more than 100 nanometer in size, which is false about dendrimers. So that's why this is the correct answer for this particular question. Is it making sense? Okay, if there are no doubts, then I'll move towards the next question. The next is we have to rank the order of clearance of charged molecules, assuming all particles are of same size and below 6 nanometer. So this relates with the clearance of particles via kidneys. So if you have read about it or attended the lecture, you'll be able to answer this. I'll wait for a few minutes for you to go through all the options and then we can discuss.
First option.
Negatively charged nanoparticles are cleared faster than neutral ones, followed by positively charged particles, owing mainly to interactions with the GBM. Okay, thanks for answering. Anybody else?
Option 3, positively charged nanoparticles are cleared faster.
Okay, then negatively ones and then neutral. Okay, we have two completely
No,
opposite
I'd
answers.
like to change my answer to the fifth option.
To the fifth one, two, three, four. This one, negatively charged are cleared faster
Yes.
than positively, followed by neutral. Okay, okay. Now we have two answers. One is option 3 and one is option 5. Anybody else? No one? Okay, we'll look at the answer then. Yeah, the correct answer is positively charged nanoparticles are cleared faster than neutral ones, which is followed by negatively charged particles, owing mainly to their interactions with GBM. So that is, I think, option 3. So one of you was correct in answering. So we'll look at what exactly is this concept. So first of all, whenever you're this, as I said, deals with the clearance of particles via kidneys. So if your particle is somewhere around 5 to 10 nanometers, it will mostly be cleared off by kidneys. So now why is that the case? Because you have this GBM layer in kidney cells which is responsible for clearing these particles. If you have a particle of somewhere around more than 6 nanometer in size, so that will be restricted because of the gap between these cells is not more than 6 or 7, not more than 10 nanometers. So if you have a 100 nanometer particle, it won't be cleared. If you have a particle size somewhere around 1 to 6 nanometer, that will be cleared because it can easily pass through these layers and be cleared off from your kidneys. If you have particles even lower than 1 nanometer in size, that would also not be cleared because there's a lot of glycocalyx lying on these cells. So your particles are so small that they will get trapped in this layer. In that case, the clearance rate will reduce. So as the question suggests, you have a particle below 6 nanometers, so that is definitely going to be cleared from the GBM. Now, not only size but the charge of these particles also plays a role in clearance of these particles. So let's see what charge has to say. So first of all, because this GBM is made up of cells, so your cells will naturally are going to have a negatively charged membrane over them. So that is why all of this, the GBM layer is the GBM, the glycocalyx and the podocyte glycocalyx also, these all are negatively charged. So now your the filter, let's call this as a filter, the GBM layer, this is your negatively charged. So what will happen if you have a highly negatively charged particle? It will be repelled by this GBM layer, so that's why it won't be cleared to that great an extent. Instead of that, if you have a positively charged particle, this your GBM is going to attract it because it's negatively charged. So that's why more positively charged particles will be cleared faster. Then will come your neutral, as it doesn't have a charge, so it will have a lower clearance rate compared to your positive, but it will have higher clearance rate compared to your negatively charged. So this is the ranking that we can do. First your positively charged particles will get cleared, then your neutral, and then your negatively charged particles. So I think that is the option 3. If we have to rank the order of clearance of these particles, positively charged nanoparticles are cleared faster than the negatively charged ones, followed by neutral nanoparticles, owing mainly to interactions with the GBM. Is that clear? Yeah, I'm assuming there are no doubts here. I'll then move on towards the next question. Yeah, your next question is, which one of the following is correct with regard to elasticity of particles? And we have few options here. Let me just quickly see. Yeah. Okay, somebody is trying to answer as option 2, which is low modulus particles can circulate longer, so they can squeeze through tissues, avoiding uptake by immune cells. Okay, we have one answer. Thanks for answering. Anybody else has a different answer? No one? Okay, let's look at the correct answer then. Yes, you were perfectly right. The correct option is option 2. Low modulus particles will circulate longer as they can squeeze through tissues, avoiding uptake by immune cells, which is which actually tells us that you need to also, apart from size and charge of the particles, you also need to look at the elasticity of these particles, because then you would want, that depends on what your application is. If you want these particles to circulate in your body for a longer time, you need to make them a little softer. If there are stiff particles, then they will be uptaken by the macrophages very easily. Instead of that, now if you have low modulus particles which are softer in nature, then they can circulate because they can squeeze through the tissues. Let's say an immune cell is trying to uptake them, they will quickly squeeze back from these gaps present in the endothelial cell layer, and they can keep on circulating in the blood for a longer time. So that's why your low modulus particles will circulate longer, as they can avoid uptake by the immune cells. Making sense? Okay, then I'll move ahead. The fifth question is, pegylation of nanoparticles is a common practice to evade uptake by phagocytic cells. Now, which one of the conformations of PEG is preferred to maximize this effect? So, several different conformations given here. We have to select which one is going to be the best if you want to avoid our particles uptake by phagocytic cells. Anybody wants to try? Okay, no one? I'll discuss the answer then. So the correct answer for this question is brush conformation. So let's look at what exactly is pegylation. So pegylation is nothing but you have your nanoparticle surface, you conjugate it with PEG chains. PEG is one of the polymers, polyethylene glycol. And what this will do is, so you'll have your nanoparticle surface like this. For example, let's take in this particular diagram, it's a liposome. So you want to avoid these liposomes to be uptaken by your macrophages, because macrophages will think that these are foreign material, so they will naturally try to phagocytose them and clear them off from your body. We don't want that. So what you can do is you can put in peg chains like this on the surface. Now there are various different conformations in which you can attach peg chains. It could be a brush conformation like this, or it could be a mushroom conformation. Now the question is asking us which would be better to maximize the effect of avoiding uptake by the macrophages. So if you have this mushroom conformation, it'll just make a bulk round of the peg chains, and since it's a long polymer chain, it is going to make round itself up and then attach it on your liposome surface. Now this will, if you have something like this, more amount, it gives scope for more amount of proteins to come and adhere to this surface. This is what we don't want. Instead of that, if you have brush conformation, which is your long chains are just lying around from the surface in this way, and they are not very stiff, they're mobile, they can just float around here, but they're very firmly attached at the base. So if they're floating around, it will act like a brush, and they will just throw off these proteins or any cells that are trying to come near this liposome. So that is why your brush type of conformation is considered better. in avoiding the uptake by phagocytic cells. So that's why option 1 is the correct answer. Is this clear? Okay, I'll move on towards the next question then. So next is, which is the working principle behind enhanced permeation and retention effect? And you have two correct options in this. So there are various options displayed on the screen. Take your time in reading through this and then we can discuss the answer. Any volunteers? No? Okay. So the correct answer for this question is positive pressure between vasculature and intratumoral environment allows flow of particles from vasculature to tumor tissue, and then faulty lymphatic clearance of particles from intratumoral environment. Now let's see what is this EPR effect, which is enhanced permeation and retention. So this effect is seen in cancerous tissue, and we can make use of this effect to deliver our drugs to the cancer tissue. So you on the screen you have a diagram which highlights the difference between normal tissue and a tumor tissue. So what happens in normal tissue is you have this tissue here, and you have your blood vessel flowing through the tissue. Blood vessel is lined by endothelial cells, which are very tightly packed, so they won't allow anything to just randomly go from this blood vessel to the tissue. This is for safety reasons. And you also have a lymphatic vessel flowing through this tissue, which will then drain out all the waste that is coming from this cell tissue. Instead of that, if you look at this tumor, you can see that the cells are very haphazardly grown. First of all, there is no organization, and then if you carefully look at the endothelial layer of this blood vessel, you can see that the compared to the normal one, it has a lot of gap in between two cells. So that is what happens in tumor tissue, because your tumor is now trying to eat all the nutrients that are flowing in the blood vessel. So to facilitate that, it will have leaky blood vessels. Leaky meaning there's a lot of gap in these endothelial cells. So if you now deliver your drugs, which are drug particles, which are your micro or nanoparticles encapsulating the drug, so now they're flowing in the blood vessel. So what will happen, since now the gap is a little bit more, your micro and nanoparticles, especially your nanoparticles, can easily flow through these layers, layer of endothelial cells, and they can now enter your this tumor tissue. So that is known as enhanced permeation, because your permeation of these particles is now a little bit increased compared to the normal one. And then what is retention? So as I said, lymphatic system is there in place to remove all the drainage, all the waste from these cells. So in tumor tissue, this lymphatic drainage is very ineffective. It is not a very good, it does not have a very good lymphatic system. So now what will happen, your nanoparticles have entered the tumor tissue, but they are not being cleared away, so they are retained inside this particular tissue. So that is known as, that combinedly is known as enhanced permeation and retention. So this is one of the ways where you can increase the delivery of your drugs to the tumor tissue. So that is why both these options are correct. This is the working principle behind the EPR effect. Is this clear to everyone? If there are no doubts, I'll move towards the next question. Okay, then let's look at the next one. The next question is, which of the following methods can be used to measure size of nanoparticles? And we have two correct options here. Any guess? Anyone wants to volunteer?
2, 3.
Second and third, that is dynamic light scattering and atomic force microscopy. Okay, we have one answer. And then, yeah, someone is trying to say, give off the same answer in chats. Okay, both of you have answered the same thing. Anybody else wants to try? Thank you for answering, both of you. Okay, no more response. Yeah, so I think both of you are correct. Yes, so the correct method that we can use to measure size of a nanoparticles is dynamic light scattering and atomic force microscopy. So the rest of the methods does not necessarily give you the size. X-ray diffraction is essentially used to know whether your material is crystalline or not, and if it's crystal, then you can get the structure of your, let's say you have a protein. That's what XRD is used for. Gene transduction is not used for knowing the size, and also ballistic gene gun mediated transfer is to transfer your gene inside the cells. It's not for size of the particles. So yeah, the correct option is dynamic light scattering and atomic force microscopy. Okay, no doubts in this, I assume. I'll move towards the next question. The next is, which one of these is not an advantage of nano and microparticles? So we have been talking about these particles a lot. So we have to select what is the disadvantage of these particles from amongst these options.
Second option.
Second is, it can elicit inflammatory reactions in host. Okay, anybody else? Thank you. I guess no response. Yeah, you are correct. The correct answer is can elicit inflammatory reactions in host. So we'll look through the options one by one. So yeah, first of all, nano and microparticles, they act as control release depot systems, which are similar to all the macro systems which we have discussed in previous lectures. And yeah, so these are injectable. There's no need for surgical implantation. Is actually an advantage of these particles. Next is, it can elicit inflammatory reactions in host, which is not what we are looking for, because if you deliver particles and it starts giving inflammatory reactions, your particles will be cleared very easily, very fast from your body, and then you won't have enough time for the drug to be delivered. Then it's possible for delivering large hydrophilic molecules inside cells is actually an advantage of these particles, because let's say your drug is very hydrophilic and you have just delivered it to the cells, and as I said, your cells will be having a cell membrane which is actually hydrophobic in nature. So your hydrophilic molecules will not enter the cells very easily, and then your therapy will fail in that case because your drug is not entering the cells. So instead of that, what you can do, you can encapsulate this hydrophilic molecule inside the particles, and the particles will anyways be uptaken by the cells, and in that way your drug can now be released inside the cell. So that's one advantage. Next, these particles can be adapted for targeted delivery to cells and tissues. As I said, these particles, as we just saw in case of tumor, that these particles are uptaken because of the enhanced permeation and retention effect in the tumor tissue. Additionally, what you can do, you can design a particle, and on that surface you can tag it with signals which are then recognized by specific cells and tissues, and in that sense you can make a very targeted delivery. Also, it is one advantage is it improves the stability of drug in vivo, because we saw the brush and mushroom conformation where you can pegylate your particles. That will then increase the stability in vivo, because it will avoid all the uptake by macrophages and immune cells. So yeah, the only disadvantage these particles can have is it can elicit inflammatory reactions inside host, which there are ways to minimize. Clear? Okay, then I'll move towards the next question. The next is, which one of the following parameters does not affect microparticle synthesis using double emulsion method? I'll wait for your response. Go through the options. Okay, Hanuman is trying to say option 1, which is polymer type and molecular weight. Okay, thanks for answering. We have one answer. Anybody else wants to try? Okay, no, I'll discuss the answer. The correct answer is actually none of the above, because all of these parameters will somewhere affect the microparticle synthesis. So let's look at all of these. So first of all, as I said, your double emulsion is one of the methods to manufacture these particles. So what happens in this essentially is, I'll just briefly go over this process. So you first have an aqueous drug solution, meaning your drug is dissolved in some water layer, and you then drop this into a solvent which already has PLG in this. So this is your first emulsion. So your aqueous drug solution is going to be in a smaller amount compared to your PLJ in solvent. And now if you vigorously mix this, because so this is considered as the oil phase and this is your water phase. So your oil and water won't essentially mix, but if you give it a lot of energy, it's going to form an emulsion wherein your oil will, since oil phase is in bulk, your water is going to find some spaces here and it's going to look something like this. So your water will form droplets inside this big oil phase. So this is your first emulsion, wherein now your drug is trapped inside this water phase and then you have a bulk polymer in organic phase. Now this is first emulsion. So to have a double emulsion, what you can do is you can take these particles and drop it into an excess of aqueous solution with another, let's say, surfactant, which is polyvinyl alcohol, and now the situation is going to be reversed. Now you have this particular particle in lower quantity compared to this aqueous phase. So now what will happen is, and then if you vigorously mix it, it will again form another emulsion, the second emulsion, which is the double emulsion. And now herein what you'll have is, since there is a lot of water outside, so you'll have, outside there is water, then you have this microparticles will form, which then have your drug encapsulated inside it. So this is how you get water oil water double emulsion. Water oil water meaning you have a bulk water phase, you have a layer of oil or your organic solvent, and then your polymer, basically PLJ. Organic solvent will then evaporate, and that is how these microparticles form, and inside also you have a water layer. So there are various parameters which will affect how these particles are made. So these are polymer type and molecular weight. What polymer you are using, in this case they've used PLG, so this could vary. So that is going to affect how these particles are made. The molecular weight will also affect it. What concentration of polymer you have put into the oil phase changes a lot of things. Your type of drug, the method of incorporation will also change the way these particles are made, and various other parameters like organic solvent, the type and amount of surfactant that you are using, in this case it's PVA, and then you have the ratio of this aqueous phase to organic solvent ratio, and then the rate of stirring, because if you stir it at if you're giving a very high energy to this system, then it is going to make more smaller and smaller particles, so that will change your particle size. Then parameters such as evaporation rate or the volume that you're using of all these polymers and these aqueous phases. So if you go through the question once again, we are supposed to identify which parameters is not going to affect microparticle synthesis, and if you go through the options, you'll see that all of these will affect the synthesis process, and that's why the correct answer is none of the above. Is it making sense? Are you guys getting it? Yeah, so I think this was the last question I had for you today. Yeah, so that's all I have for you for this session, and if anybody has any doubts or wants me to repeat any question, I can go through it again, and if not, then we can meet next week. So next week my session will be on Monday 6 to 8. So in that we'll then discuss the 5th assignment. Does anybody have doubt here? If not, then I'll end the session.
Thank you.
Okay, thanks for joining.